Okay, so I'm glad to be here. Great to see some familiar faces, great to see some new faces. So today I'm going to talk about probabilistic programming, and I'll echo the same message that Hansog said. Be careful. So let's start with a very simple background on probabilistic programming. So let's say we have a very simple probabilistic model, something we can study in high school. Like we have a coin, we want to flip it. We model that as a Bernoulli probability distribution, right? So now if you want to know a distribution that A resulted in head is 1, tail is 0, you get something like this, right? This is what we think about probability distributions. Now, here's a quick question for you. What happens if we toss 3 coins and we care about the probability of the first coin? How would this distribution change? It won't, because they are independent. But let me take a little bit more complication here. So what happens if we know that at least 2 of them resulted in a head? And we again write it in math notation like this. Do we expect the distribution to change? What's more likely, to be head or to be tail? Or you flip a coin and tell something. Head, yes. And here is how the probability looks like after we know this additional fact. And this is what we call posterior distribution. And what we started from was a prior distribution, our initial belief before knowing the fact that at least 2 of them were heads. Now we get the posterior one. So this is all math so far. Where does programming come into place? Well, probabilistic programming gives you a nice interface to represent various probabilistic models. So you can express this probabilistic model using code notation. And this is really similar to what math would say. So we have sampling from probability distributions, we have observed to describe conditioning, and finally when we return, we ask for posterior distribution, right? So now, power probabilistic programming is that really the code represents the distribution, but it also gives us an advice how to perform the computation. As you may have seen the Pyro implementations before, they are very tied to how we would compute the result. And so far, you know, this looks like a trivial task. However, when we think about implementations, there is typically a probabilistic programming system that lies in between the probabilistic model and the result we want. So typical setup is there's a model, there's some observations that at least 2 coins resulted in a head, and there may usually be some parameters of the system, and finally we get estimates for the values of the parameters as our results, right? So in principle, computing probabilities is simple. We just apply Bayes' rule, and we get what we want. But real life is more complicated. And what these systems typically have is a combination of various components. So we have front ends, optimizers, various APIs, multiple inference algorithms, numerical libraries. It may be implemented on PyTorch or TensorFlow, and just increase the complexity as much as you want. And it's not uncommon for even for probabilistic model as simple as this one that when it executes, when we need to get the distribution, we touch more than 5,000 to 10,000 lines of code in the underlying system. So this is really an exercise in complexity. Now this, of course, from all of us, when you put back the software hat on, the question becomes, okay, how are these systems, are they robust to bugs? And what can happen if, system is a little bit broken? So here's some things that can happen. You may get runtime errors, that some tensors are wrong. You may get numerical errors. You really get some parameters that are NaN, some others are infinities, and so on. Or you may just have inaccurate results. And now, good luck finding those. So in this talk, I'll focus on a more practical side of probabilistic programming and looking into what happens with the systems, what kind of bugs exist there in the wild, and how can we improve the reliability of these systems. Now, let's take another close look at this workflow. So what do we have? We have some model, we have some data, we have a system, and we have some results we care about. So again, putting our software hat on, what does this remind us? Okay, what would this remind us of? Well, what about compiler? Well, we know how to test compilers. There are various works, including CSmith, including EMI from Zhendong's group, and so on. But okay, compiler takes source code, produce some other source code. We here have a result. Then maybe we compare this to virtual machines. Again, same kind of techniques apply there. Or we can think of this, this probabilistic model. It's really something very high level, which can resemble, say, SQL queries. And then there is another analogy where the system may look like a database system. So actually, I did not find much work there, existing work. But I hear there will be some interesting talk this afternoon, and I'm looking forward to hear it. So anyway, so what are the key aspects here? The key question is how do we? People have used fuzzing for various domains. But what changes when we think about probabilistic programming? So one thing is we have distributions, we have randomness, and we need to think about accuracy. But here are few things that we need to think about. So let's try to sketch out a way how we can try fuzzing probabilistic programming systems to find possible bugs. So we would start say from some seed inputs and generate a bunch of programs. So we have a component of the program generator, then we get programs. Now it turns out there are various probabilistic programming languages, and they have different syntax. So, it's easy, just have multiple translators. These are three popular ones, the three systems, Stan, Edward, and Pyro, so each of them has its own syntax. All right, so we have a program for each one of them. Very good. Then, as what we usually do with testing multiple systems, when we don't know the reference solution, we can go and check one against the other, and we may find the bug or not. Something that indicates that we should look at some of these programs. So, I could have made a slide for almost any other domain. But what are the challenges that happen in probabilistic programming? Well, first thing is when we do random test generation, we need to know something about both distributions and inference mechanisms to produce meaningful programs. Because if you just start doing things randomly, you may not get far, because these models at the current state and the way how the tools are implemented, you need to be careful in how you construct. Now, another challenge is when we look at what we produce out of program generators. So it's not just a program. It's both program and the data that we need to generate. So we need to generate model and we need to generate observations. Then when we think about translation, well, each probabilistic programming system has its own custom domain-specific language, all specialized inference engines and programming models. So Stan is quite different from Pyro, which resembles Edward, but not exactly. And then what are the properties we may want to check? Well, here are a few. We may need to account for stochastic nature of inference algorithms. As we've seen in Hongshok's talk, these problems can be very nasty, and we need to compare distributions rather than just saying, "Oh, this is the same as something else." So this brings a little bit of noise in the whole process. All right. So to address these issues, we started developing systems for testing probabilistic programming systems. So our first system is called ProbFuzz, and it automates fuzzing for probabilistic programming systems and tries to answer these challenges. So what ProbFuzz does, it defines a common intermediate language for representing probabilistic programs and allows manipulation on their structure. Then it also exposes partial programs, or so-called templates, to the developer, so they can target program generation in a specific way. So if you care about something like linear regressions or regressions in general, you can write partial model to specify that this is what you really want to test on. Then what we encode inside profiles is domain knowledge for code and data generation, and support it with some program analysis. And finally, we connect accuracy, reasoning about accuracy inside the process of differential testing. So what are the results? Well, the results were fairly positive, and we got more than 50 new bugs in these three probabilistic programming systems, Stan, Edward, and Pyro, and also their underlying frameworks, TensorFlow and PyTorch. And we also were able to reproduce some of the existing bugs that the developers already knew about. All right. So you may wonder why a common IR? Well, as we said, each probabilistic programming system has its own design, syntax, and there is lots of variety. Everyone who introduces a new probabilistic language has their own syntax. It has their own set of assumptions. And if we want to go from one probabilistic programming system to another and try to compare them, well, we need to have relatively easy interface to do that. Duplicating all the work maybe too much, so having an IR allows us to have a common implementation of many steps for the analysis and transformation, these probabilistic programming systems. So how does this IR look like? Well, if you've seen any of the papers on probabilistic programming, this will look very familiar. So it's just like pseudocode that most of us write in the papers. So what do we have? We have mathematical expressions, we can have assignments, we can have sampling from distributions, conditionals, for loops. Then we also have observed statement for conditioning that can encode both conditions and factors. And the key aspect for building our templates is having holes, which specify that some part of the structure may be missing. And it's also familiar to those of you who have seen program synthesis and sketching. So for instance, here we can say that the distribution of W may be something that we will fill in, or we may put that also for parameters that, this is normal distribution where this is mean and variance is unknown. And finally, the language can express probabilistic queries, like asking for a posterior distribution of some of the parameters or its expected value. So with a language like this, we can represent a large number of common models. For instance, very large number of those that come with Stan repository, and models can be linear regressions, hidden Markov models, so on. So here is how you can think of generating a template. So here is an example test program. So let's say we have linear regression, right? So how do we define linear regression in probabilistic programming? Well, we need to have some data set, like values x and values y. This is kind of relationship we want to test, and we want to estimate uncertainty around that. So we start with some prior distribution. We express some assumptions about weight and bias. Then here is how we specify conditioning on the data. And finally, we want to know posteriors of the parameters, which can tell us both what's the most likely one and how much the noise we have around. So if we want to test our probabilistic programming system on a set of models of this kind, here is how we can proceed. We would write a template that would make some points changeable. So you can change here priors, you can change here, for instance, variance, and also the distribution in the observations. And we can plug it in the generator, and generator can start churning out one program, another, or for as many programs as you want. All of them will be different, have different parameter values and different distributions. So let's dig a little bit deeper into this process. So when you specify template, first you can specify a way how to generate data. You can have more or less flexibility in that process. So we can say, for instance, hey, we want data to have, in this case, 10 floating point numbers. W and B here will be constants, and they will be hidden. And finally, y will have this linear relation with x. And we can get a result like this. So if you see this kind of relation, is there something wrong here? Well, what's limiting here is y is always equal to 3 times x plus 0.1. So you can also specify that when you generate data, you generate it with some noise. And now this is hidden from the model itself. This is just data that we sample. Now the model itself can have specifications where now we have variables weight and bias, right? That are unknown. And can we fill any random distribution in here? Not really. And we'll see that we'll need to do a little bit of analysis to figure out what are good values for it. So, and we'll especially see it here. So let's say we want to fill in that spot in the observe. So we pick a distribution that has 2 parameters. One that we're familiar with would be normal. So with normal distribution, what do we know about it? We know that its support is anywhere on the real line. Mu can also have any value, and variance can be only positive. So this also means it puts some constraint on this value here. And now we can make a choice of whether we want to generate legal programs that have legal variance or some that are not legal. And we'll see that this is a very interesting choice we can have as errors that happen at the boundaries are pretty common in these systems. So this is one way how we can generate the program, and finally we ask for posteriors that we can go and compare later on. So this is now template. This is a program that we generate out of it. Next step is we go and translate this program into the code of each probabilistic programming system. You've seen in the previous talk how it looks like for Pyro, and there is lots of complexity in composing those different APIs and writing everything together. So for each of them, you need to translate, and then you need to run the translated programs on each system. Once we get the result, then we go into checking. So what are challenges in translation? Well, just different syntax for every program, and we just need to make this step go through. Funny enough, even though you may think automatically transforming from one language to another may not be yield optimal results. Note here one thing: probabilistic programs are usually small in size. Some patterns are very similar in different languages, and actually we compared the programs we generated for Pyro with those that Pyro developers manually transformed from Stan. Yes, Rendong.
So how do you get the templates?
So template is something that a tester would write. So for instance, you care about certain classes of models, and part of the reason why I say only certain classes is when we come to checking whether they are accurate and so on, we kind of want to start from something that we're more familiar with. And we take this step at a time. So this is something that a tester has some experience what they want to know about, and they just start from, they usually start from a seed program, and they say, I want to change this, this, and this.
I also support Hamiltonian Monte Carlo. Mm-hmm. So you didn't translate it with Hamiltonian Monte Carlo?
Oh, we tried multiple inference engines. So did not always look with the Hamiltonian Monte Carlo. So this translation, we looked at what, for example, actually we did it in parallel with them. So after the fact, we just looked, oh, you guys translated the same way we did. So that was enough for us there. But this is a good point. Like, these languages have multiple inference engines, and each one of them may have some funny things going on. So we'll see that in a couple of minutes. Then we get into fun part, checking. We got results, we got posterior distributions out of each system. Now we need to check it. Well, maybe we didn't get distributions. Maybe some of the programs crashed. Maybe some of them did not complete it until the timeout ended. For example, failed to initialize Monte Carlo simulation or so on. Some of them may have numerical bugs. And finally, some of them may have problems with accuracy, or we see differing accuracy between different systems. So, how do we think about accuracy? So here is a simple example. So here below, you have one generated program and the result from 3 systems. These are the posterior distributions. So find an outlier. So I'll come back later on what's going on here. But for now, what do we need to do? We need to compare distributions. What are 2 problems? Well, what is the correct result? How do we get the correct result? And also, how do we compare even when we have just different approximate results? So how can we get reference value? Well, one way is run exact inference, like Psi. Other is, when we generate the data, sometimes we know the relation. You remember when in linear regression I said, here's how we generate y is equal some constant times x plus some other constant plus some little bit of noise. So you kind of expect that values would be around 7 in this case. Or we can just go and compare the result of one tool after another, but for that we need to define some metric. One metric for comparing distributions can be KL, as you've seen in the previous talk. Another one can be, say, you're just comparing the means. And in our case, we did different metrics for different templates, and this is something that's fixable. In this case, this was a nice one for us because it always gives results between 0 and 1. So differential testing in this case now becomes you compute expected values and you start comparing. Are those, here, there's not too much difference. And the reason, by the way, the reason why I have multiple points here is like we can have multiple posterior distributions for multiple parameters. So for each one, you put expected value in here. So, here we have only one posterior, so these 2 match. Small difference. These 2 don't really match, these 2 also don't match. So the tool would say, hey, check this out. Stan may be a little bit different than the others. All right, so these are kind of the components. This is what the system would give you. Now, what do we find in practice? Well, we tested prop fuzz on three systems, and we used 4 templates: linear regression, multiple regression, simple distribution fitting, and conditional models. For each of these templates, we generated 1,000 programs, and we categorized bugs in 4 classes based on error and bug manifestation. And this comes both from errors we found here, but also we did a full empirical study of all existing bugs at that time in these 3 systems. So we look at all issues, all commits, and found what developers really saw as bugs. And it turns out that domain-specific bugs contribute to about 1/4 of all bugs in these systems. And they can fit into these 4 categories: algorithmic or accuracy, dimensionality or boundary value bugs, numerical errors, and language and translation bugs. And here's how they can be manifested. So this is our experience of finding new bugs. So it turns out we found bugs in every system, and the total number of bugs is about 67 that we found. But we sent issues and messages to the developers. Developers accepted 51 of them, rejected 8, 7 were still pending, and 1 bug was fixed in parallel as we were running these experiments, so nothing to report. Now, we looked at what these bugs did, and as we dive deep into what's going on, we actually were able to come up with fixes for 50 of them, and developers then went and fixed 1 bug on their own. And I'll come back in a couple of minutes with examples of what the bugs in the wild look like. The second question you may be wondering is, how much does probabilistic knowledge help you? So for that, we compared prop fuzz with it has the probabilistic domain information in when it generates programs, with the one that would just generate programs from the grammar. And Each cell here contains the percentage of programs out of 1,000 that produce a legal numerical out of the program. So when you don't have domain information, most of the programs will either stop at the parser level, because it's not really something it can deal with, or it would result in errors like boundary errors. But then when we fix all the boundary errors, we cannot really progress further without domain information. With domain information, for every language, you can get much higher probability of getting and executing more components of the underlying system. All right. So then we learned several lessons from studying these bugs, and these lessons are really going to confirm this message: be careful. And there are many places where things may go wrong. Some of them harder, some of them simpler. So first lesson we learned is that dimension and boundary value bugs are often found in probabilistic programming languages. You can see here, 13 in Edward, 41 in Pyro, 0 in Stan. And this is really proportional to how mature these systems were. So at that point, Stan was the most mature, Edward was somewhere in the middle, Pyro was just released. So how do some of these bugs look like? So here's one example. Can you spot a bug? And I marked it as yellow. So we have Bernoulli distribution is probability 2.0. So and probabilities can go only between 0 and 1. So you know what you get? You get a number. What does that number mean? Something. But it's not really something that's useful. So can some of you suggest a fix for this kind of a problem? Well, just add a check for boundary condition. The distribution is between 0 and 1. All right. That was a warm-up. Now here's another problem. Can you spot the bug here? We run this program, now we have normals, stuff, and then we get division by 0 error. And it's not the same division by 0 that Contract was talking about. So, anyone spots an error? Well, the error is somewhere deeper. So what went wrong? So it turns out that there is a missing check for one of the parameters in the Adam optimizer, and crashes when that parameter is outside of the range 0 and 1. So first we needed to go into the optimizer, figure out what was going on, and also look at the theory behind it. So what do you need to do? Well, we said you don't just look at the code, you also look at the paper. What's in the paper? Very nice specification. Beta should be between 0 and 1. So that's another check we need to do. And by the way, this was not bug in Pyro itself, it was bug down in PyTorch, which also tells another lesson we learned, that fixes might extend across the boundaries of individual systems. And in fact, driven by observations on different boundary errors, we also look into finding a more general way for testing for those. So we found these bugs, and we also proposed a global fix that would say, hey, why don't we have an argument that validates errors and see, like people can always check that distributions are in the right range. And actually PyTorch developers liked it. And following this fix, Pyro also introduced a flag for boundary value checking in the next version. Before I go to the next one, by the way, you know why Stan had 0 boundary value bugs? Because if you look at their repository on GitHub, you will see an always open issue that says, always check for boundary conditions for every release. So they are painfully aware that these errors happen. All right, and then let's go back to accuracy. So this was the example I showed you before. So we did another check. We ran the same program in bugs, which is a classical system for probabilistic programming. It has about the same syntax as Stan. And what was the problem? Well, it's actually a problem in usability, where Stan has a little bit different interpretation of sampling statements. And what you need to do, you need to set the interval explicitly in the source code. If you don't, you may not get the best error message, and it will not point you directly to the problem. And by the way, bugs would produce the correct result right away. So this also gives us another connection with something we know for a long time. Whenever we analyze compilers, program analysis, having good methods and guiding developers in the right ways is an important aspect, and something that we as community have a lot of pain in the past and still trying to figure out. So this is then the first checkpoint. We had a bunch of other cool results in the paper. And by the way, the database of bugs is also available if you want to take a look at what problems existed before. So you can see old bugs, new bugs. And the tool itself is open source. Now, for some of you, again, if you put your software hat on, you may ask a question, sure, we generate these programs, we kind of know the models, but can we do even better? Can we even try to localize things a little bit closer? So let's take another example. Yeah.
I had a question, like a couple of questions quickly, because I'll forget after. But so the first one was like, one thing I kind of want to understand is like, if I have a probabilistic program and I'm running it on some inference system, then I take this probabilistic program and I transform it into another one which should produce an equivalent distribution by construction. Mm-hmm. And then you're just checking whether because then you're not changing the underlying system. Did you look at this, or it's always like across systems?
That's a very good question. Yes, sometimes we looked, for example, Stan has 4 or 5 different backends. We looked at them, not in an official full-blown experiment, but that is another way how you can test some of these things. There's also another way to test it, and I'll come to that in this next part of the talk, is you can get different versions of the same system and try to see whether some code works in or distribution is computed well in one version, not in the other one. But this is a good question. With this single system, you can go and find certain categories of bugs. But if the bug is, for instance, in something that's like this Bernoulli 2.0, it will happen in any inference engine, right? So it's kind of like you need to go a little bit around for some of these problems. Sorry, Martin, you have another one, or Zhendong?
Oh, go ahead. Yeah.
Oh, just an even more basic question, right? Have you applied, for example, things like AFL on this?
Sorry?
Have people applied AFL? Like this kind of like just coverage-based fuzzing on systems. Yeah.
That's a very good question. So the thing I showed here before, not directly. However, here is the result that may lead to what. So this is the result that kind of lead what AFL and similar tools that would just generate programs would yield. We did not talk about coverage here. The thing about coverage, here's also another fun thing there. Not all paths are equally valuable, though, and many of conditions that you encounter would require knowing something about numerical properties of the data. So AFL directly, I'm not sure how well it would work, but the works that are trying to look at numerical constraints with floating points would probably have a better result. But this is a good question for going forward.
Just quickly follow up. And I guess with AFL, you probably can find a lot of the dimension-related errors, right?
Yes. Yes, and even with this one, it's like it would stop at some point, and these errors would be. These are kind of like sort of easy hits, and many of systems would be able to catch those. Now, what I was showing here is how do we go past that into something deeper, and trying to drill down in really into details of inference engines and program. But this is a very good question. Any other question at this point? All right, so let me move on to the next part. And now, being next on our software hat, well, here is one issue that a Stan user gave to developers. Can anyone tell me what this code is supposed to do? what probabilistic model it represents?
LBA.
Yes. Why do you say LBA?
What topics?
Exactly. However, there is also, quite some lines of code, and this is, not a trivial model, and also there is some data. And the user also reported what engine it used inside Stan. This was a variational engine, and how many iterations they tried. And they wanted to get a result. All they got was a very helpful error message. All right, so when you get an error message like that, you start wondering, where's the problem, right? Is the problem in the code? Is the problem in the data? Or is the problem in the inference parameters, or maybe in the implementation of the underlying system? So you need to drill down and look at the code, try to figure out, are you really implementing LDA correctly? Let me show you another program that reveals the same error. What is this program doing? It's taking a single sample from a Dirichlet distribution. And it has only these two values for beta. This is it. Fewer number of iterations. So what's the expected result? You go to Google, you type Wikipedia, you find the expression for the distribution, get the betas, take the calculator. Here is your reference solution. So you should get this, not an exception. All right. So it turns out the problem was not in the program itself. The program was somewhere in Stan. So some of you may already know where this is going. The question becomes, how can we help developers and simplify programs like these automatically? And this again follows the same tradition in compilers, right? For sysmit we have creduce. For EMI we have HDD and persys. So then for probabilistic programs we again apply domain knowledge, and this is the work that we recently presented at FSC this year. So we start from code, data, and inference parameters, and we want to get smaller code, smaller data, and smaller inference parameters. This is unlike compilers who typically just have code and smaller code. So what are the key properties of Storm? Well, it applies a little bit of program analysis to guide the minimization, and uses domain knowledge in how to continue that process. All right. So in total, Storm helped reduce 47 bug-revealing programs from Stan and Pyro. What is the architecture of Storm? Well, it follows the same line of thought as ProbFuzz. So it takes properties of distribution specifications, and it also defines transformations that deal with probability distributions and parameters. I'll come to that later. It also specifies different transformation orders, like sorting by cost of program analysis, or sorted by probabilistic then standard, or standard and probabilistic, or some combination thereof. And it turns out this kind of does not affect the quality of minimization that much, but it affects how fast you get there. And by the way, when we looked at this program that I showed you here, this minimization, we tried it also with DD and HDD. DD did not give anything after 3 hours. We were just starting removing character by character. HDD got a relatively similar program. It would still have while loop around the work topics, but it took 2 to 3 times more than what we did with Storm. So, and it also did not change anything about data or inference parameters. All right, so we could have gone and applied this system on each probabilistic programming system independently, like Stan or Pyro, but again, duplicated work, and we would need to implement everything again. So what we did was we reused the same idea that we had in ProbFuzz. Let's have a common IR and extend it to support a wider set of programs. Plus also, ProbFuzz was only going this way, from IR to transformation, because it starts with template. Here now we start from code, go from one language, and go back to another one. And now you can also have cross-compilation from Stan to Pyro or vice versa. And by the way, after that, we also got a couple other languages like C, and there is more work on Edward. So there are two transformation groups in Storm. The basic ones, something that you can see in works for reducing programs in compilers, and also probabilistic transformations which use properties of distributions, mathematical functions used in statistics, and other domain-specific information. So there's no surprise on this slide. It's just removing program statements. So nothing really specific to probabilities. Here are a few probabilistic transformations, like removing parameters of distributions, where we need to know. It was, let's say, variance. It was a constant. Now it was a variable. Now let's make it a constant. Or it was an expression. Let's make it a variable. What's the range? Are we fitting there? How do we? What's the dimension? Is it an array or is it scalar? And similar questions. Other interesting one is using, say, distribution simplifiers. Because if you want to get reference solution, we are used to distributions like normals, uniforms, so on. So, for instance, if you start putting the Dirichlet distribution in C would not be happy about it, but it will be much more happy with something like uniform. Then you can also have the transformations on data, and there's no big surprise here. When we have unused data, we remove it, or we can just start removing specific data items, which we will just subdivide the data into smaller chunks. Finally, for inference parameter transformation, we started using, and you can really think of that as a binary search. So now, the algorithm itself is again something that's not surprising. We try applying transformations iteratively until we reach a fixed point solution. So in every step of the algorithm, we start from some transformation order. Let's say we start with Bayesian transformation, then probabilistic, then data, and so on, and try applying each of them on every location where it's applicable. And we go until there is a full round in the transformation order where there is nothing we can do. And after every transformation, we would also do a little bit of analysis to make sure that all programs that we generate are valid and that they can immediately run on these systems. So the checker itself, in this case, we are looking for bugs that cause program to crash or expose different exception strings, have timeouts and so on, and it just returns true or false. Accuracy bugs are a different beast. I can talk more offline. So for evaluation, we looked at several questions. Here are the two that we'll quickly see. So the metrics that we looked at, lines of code, and look, these programs are typically small, so we have only few lines of code typically, but all of these programs are quite dense. So we also look at non-terminal language constructs. We also look at data size, and look at number of iterations. Here are the metrics for comparison. We use the SRR for code, where it can be either difference between either lines or the tokens in the original code. For data, it would be a relative difference in data size, and for iteration, the difference in iterations. Well, we use the programs from two sources. First, you remember that bug database? We took all Stan issues from there. We also took Stan and Pyro examples. There is actually a nice database of 367 Stan programs. So we translated them both in Stan and Pyro and looked at programs that result in an error in one version, but produce a nice result in another following version of the program. So that gave us some more test cases. And these are typically larger programs than this, because here the users would usually try to nail down where the problem may be. Problems are typically small, about 50, 60 lines of code, maybe even less. But they have dense structure. You have seen some of those programs in the previous talk, how dense the structure can be. Well, the results were positive, so we were getting relatively large reduction in both code, data, and iterations. And we also looked at what are the impacts of different probabilistic transformations, where they helped in every aspect. So this is this part. let me just say, we used this kind of infrastructure to nail down more interesting problems that we can talk offline, like predicting hardness of probabilistic programs, thinking about robustness and the sensitivity of programs to noise in parameters. And let me just say at the very end that what probabilistic programming does, it brings practical benefits and rigor in Bayesian modeling through a combination of people working in machine learning, people in programming languages, people in verification, software engineering, and so on. And it's, from my personal perspective, it's a very nice playground for thinking about uncertainty in computation, how it emerges, how it propagates. And what we need and what we're getting to is more practical tools to improve robustness of both models and implementations. Now, this is just one part of the stack. The rest of the stack is you can think about uncertainty in all parts of the stack, and this is what we're working on in my group. So we had some luck with some papers, and if you ask me what are we doing right now, well, as I'm giving this talk, the students said they're hard at work. So this is what's going on in Illinois. All right. All right. Thank you very much, and I can take any other questions, and I think next is coffee break.
Okay, thank you.
So the second part of the work, I'm just wondering, like, why is it useful to do these like program reduction transformations in a common IR? Like, I don't know each like runtimes like capability in terms of compiler optimizations as well as but does it overlap with like these compiler optimizations done by each like
not much not
probability program is like because I could imagine they'll probably just do some transformation as well as some optimizations within the runtime too.
They do.
Right?
It wouldn't be classical optimizations, and to be honest, catching how different systems implemented different parts, and for example, some systems may go and transform the computation in continuation passing style, like WebPPL. So now we need to go and dig in there to find a spot where to do our transformation. So we found this is a cleaner method not to duplicate. I see that we may be duplicating work that other people have done in different contexts, but finding where different implementations may have done parts of this work and connecting that together, that was something that we wanted to avoid. So doing everything in every system independently.
But I guess another question is like, what is the power of doing it in this common IR, right? As opposed to doing it in each, right? Like, I mean, not the work overlap,
Yeah. So, well, short-term short-term benefit was that we were able to define one set of optimizations, and they would always behave the same. So we could even have for the experiments the same kind of reduced programs. But longer term is we're now able to go to cross translate between different languages, and also do some other kind of more expressive analysis that we wouldn't be able to do if we did everything in a single language. So right now, it's becoming more of, hey, we can now have a joint infrastructure that supports analysis and transformation of probabilistic programs. That's not always tied to the syntax.
So let's take a last question from Chendong.
Yeah, just a small technical question regarding the reduction part, right?
Yes.
So Sasha, do you have any sort of minimality guarantees?
Not really. So I would say this is still the best effort fixed point algorithm. So it will reach a local minimum, but will it reach the global one? We do not have guarantee of that sort.
Okay, so thanks again, Sasha.
Thank you, Peter.